Welcome to the third tutorial of topic 3 formulae, stoichiometry, and the mole concept. So in the last tutorial we had left off at the deducing empirical formulae of compounds. We had seen an example of an oxide of phosphorus, right? So now you might be asking why I put this hanging on my wall to this point, right? So there's a reason to it. The reason being this is your empirical formula, right? This is not your molecular formula. Whatever you calculate, whatever you get from this process, from this system, from this technique, from this calculation is not your molecular formula. However genuine or however legit this might look, this isn't your molecular formula. This is your empirical formula. And in order to calculate your molecular formula, you still need your N. You still need to know how you need to know the factor by which you've simplified your molecular formula, right? Right. So yeah, that's that. So this is the reason why I've kept it here. For instance, you've somehow come to know that the N is 2, so the molecular formula is going to be like P4O10. So yeah, that's that. Right. So let's have an example, or let's take a look at how we put this formula, this MF equals N into EF, how we put this formula to use, right? All right. Now consider just a moment. Let me. Okay, right. So consider the question: a compound has an empirical formula of CH2Br. This is the empirical formula of this compound, and the relative molecular formula of this compound is 187.8. The question is, deduce the molecular formula of this compound. So what you're provided with basically is you're provided with the empirical formula, you're provided with the molecular formula, and now you're asked to calculate the MF, right? You're provided with your EF, and now you're basically asked to find your MF, right? Right. So before we jump to calculations, what I want you to understand is relative molecular mass, this relative molecular mass comes from the molecular formula itself, right? This is very crucial. This is very crucial to understand. Understanding this is really crucial, as this will help you solve this problem. So what you need to understand is relative molecular mass comes from the molecular formula, right? So relative molecular mass comes from the molecular formula itself, right? From the MF itself. So what we will do now is we will calculate the molecular mass of this empirical formula. We already have the molecular mass which belongs to the molecular formula. Now we will calculate the molecular mass which belongs to the empirical formula. So what we will be having is 12, which is the AR of carbon, plus 2 into 1, which is the AR of hydrogen, plus bromine. Bromine is probably 80. Bromine is 80. Yeah. So 80 plus 80. So add all that up, you'll be having 92, and this will be having 94. You'll be having 94. So this is your molecular mass of your empirical formula, and this is your molecular mass of your molecular formula. So we can consider this as our MF, right? Since this is something coming from the MF, so we can conclude that this can be considered a part of the MF. So we are considering, for this problem, we're considering this as our MF. Similarly, this is coming from the EF, right? So we can conclude that. So this is coming from 94 is coming from the empirical formula, right? So we can conclude this. We can call this as our EF, right? Now what we will be doing is we will be using these figures 94 and 187.8 to calculate N. I hope it's pretty clear to you all now, right? So MF is 187.8. MF is our MF is 187.8, and our EF is 94. So if we want to calculate N from here, it'll be like 187.8. I hate this. 8 divided by 94, right? So it'll be 1.9978 to be precise. Not 1.9979. So 1.9979, which can be rounded off to 2, right? So our N basically is 2, right? So we have calculated our N. Now we've been asked, our target is not to find the value of N, but to deduce the formula of the molecular formula itself, right? So now that we know N, it's pretty easy for it'll be pretty easy for us. All right. Since it'll be pretty easy for us to deduce our molecular formula, since we have our N now, and since the molecular formula equals N multiplied by the empirical formula, and the empirical formula we have at hand is CH2Br, we'll just multiply it by N, right? The molecular formula, since the molecular formula according to the equation is N into MF, N multiplied by NF, so we'll just multiply as N into EF, sorry, MF equals N into EF, so we'll just multiply this EF, which is CH2Br, with 2, which is our N. So 2 into CH2Br will be giving us our MF according to this formula. So our MF will be C2H4Br, yep, you guessed it, Br2. Voila. So that is our molecular formula. That is how you deduce the molecular formula of any element using this technique, using this thingy, right? So you first calculate so this is where your molecule, this is where the usefulness of empirical formulas come in. When you have the empirical formula and when you have the molecular formula, you can use it to calculate your actual original untapped, unharmed, untampered version of your untampered formula. I mean, you can have the original formula. So basically what I meant to say is, if you have your empirical formula, which you'll be able to calculate using the process I showed you earlier, like making that table and all that, and if you have the molecular formula, the molecular mass at hand, which is 187.8 in this case, you can use the both to calculate your N, and then use the N in turn to calculate your molecular formula, the original formula of the compound, right, which is this. So this is our answer, and that's where our that's where this objective of ours ends. So just a moment, clear the screen. Right. So let's move on to our great. All right, here we are. Here we go. So we just calculated we just finished this. Right. So now we'll be before moving on to I, we'll be going into the mole concept. Right. So as I said earlier, as promised earlier, I said I'll be moving on to the mole concept, and here we are, as promised. So what exactly is a mole? A mole is, we saw that sodium has an AR of 23, right? Simply put, a mole is an amount of an element equivalent to its AR. I'm sorry, that's terribly explained. What I mean to say is, a mole is the amount of an element, of a particular element, which will have a mass equivalent to its relative atomic mass. So basically, 1 mole of sodium is the amount of sodium that you'll be needing, which when weighed will have a mass of exactly 23 grams. Let's move to another example. Calcium of 40 AR. So 1 mole of calcium is the amount of calcium that you'll be needing to have a mass of 40 gram. So basically, 1 mole of calcium is the amount of calcium that you'll be having when weighed will be having a mass of 40 gram. The amount of calcium when weighed will have a mass of 40 gram. That exact amount is called a mole, right? So consider it as such when you have a box of nails inside, and like there's a certain number, for instance 20 grams. So when the mass of this box containing, when you're putting in nails inside every moment, so when the moment this box combined with the mass of the nails inside will reach a mass of 20 grams, you will call it 1 mole, or 1 mole of box, right? When this will reach 40 grams, which is twice its number, you'll be calling it 2 moles of box. So basically, if 1 mole of calcium is the amount of calcium required to have a mass equivalent to its AR, then the amount of calcium required to have twice the mass of its AR, which is 80, is 2, right? So basically, if you want to know how much calcium you need in order to have a mass of 80 gram calcium, it's 2, because you just simply multiply your AR with 2 and you get 80. Voila. So I'll be going through that once again. Mole is nothing but quantity, an amount of something. So that something is our element or compound in cases. So what exactly is a mole? A mole is amount, for instance, let me give an example of sodium. 1 mole of sodium is the amount of sodium that will weigh up to that will have a mass equivalent to its relative atomic mass. So once again, 1 mole of sodium is the amount of sodium that will be having a mass equivalent to its relative atomic mass. Basically, the amount of sodium that will be having a mass of 23 grams is 1 mole sodium. The amount of calcium that will be having a mass of 40 grams is 1 mole calcium, right? So here as well, 1 mole calcium is the amount of calcium that'll be having a mass equivalent to its AR. It's called 1 mole calcium. So 1 mole calcium will be having 40 grams a mass of 40 grams. 2 mole calcium will be having a mass of 80 grams, right? 3 mole calcium will be having a mass of 3 mole calcium 3 moles of calcium will be having a mass of, you guessed it right, 120 grams, right? And so on. 4 moles of calcium will be having a mass of 160 grams. Yeah. So that's the mole concept. Now let's move on to a compound. I'll just end the conversation. I'll just end the discussion there. Right. Let's move to a compound. Like let's move to our old pal sodium carbonate. Right. Yeah. For instance, there are 3 moles of sodium carbonate here. So as seen from our first example, as seen for the first example of our second tutorial, the total the formula mass, relative formula mass of sodium carbonate was added up to 106 grams, right? So, according to the mole concept, the amount of sodium that will have a mass equivalent to 106 gram is 1 mole sodium, right? 1 mole sodium carbonate, right? I'm repeating that again. I'm repeating that. The amount of sodium carbonate compound that will have a mass equivalent to its relative formula mass is known as is known as 1 mole of sodium carbonate, right? It's just you'll just put relative formula mass in place of relative atomic mass, right? So the amount of sodium carbonate that will be having a mass equivalent to its relative formula mass, aka 106 grams, is known as 1 mole of sodium carbonate. So the amount of sodium carbonate that has a mass of 106 grams is known as 1 mole of sodium carbonate. So here we have 3 moles of sodium carbonate. So if 1 mole of sodium carbonate has a mass of 106 grams, 3 moles of sodium carbonates will be having a mass of 3 into 106 grams, right? Which is 318 grams. I hope that's clear, right? So when we have 2 moles of sodium carbonate here, if 1 mole of sodium carbonate has a mass of 106 grams, 2 moles of sodium carbonate will be having 2 into 106, which is 212 grams. I hope that's pretty easy and it's pretty understandable, right? So this basically, mole is nothing but a mere quantity. You don't need to be too scared of it. You don't need to be scared about it, right? You need to be too jumpy. All right, let's move on to our next content, I. So I asks us to calculate stoichiometric reacting masses using Avogadro's laws in calculations involving gas volume. 1 mole of gas occupies 24 dm cube at room temperature and pressure. Calculations involving the idea of limiting and all that, right? So we'll complete and go to the rest of the syllabus the next tutorial. Thank you for bearing with me so far.